Hey everybody. So today we're going to talk about salts and how salts may have an effect on the pH. We've done acids and bases, strong and weak acids and bases. And it turns out some salts will have an effect on the pH, and we need to figure out when we can recognize which salts will have an effect. So here we go, talking about salts. So the key here in terms of when a salt will have an effect, that idea is if one or both components of the salt, and when I say components, I mean the cation or the anion, end up being a weak acid or a weak base, then their presence will affect the pH. So if you end up with a weak acid or a weak base, they can do a little side reaction with that water and maybe generate some acidic conditions or generate some basic conditions. So we're going to talk about how we can figure out what's going to happen here. Some steps to approach the problem. And with practice, you'll go through these steps quicker. And with practice, you'll start to recognize ones that you don't even need to write out. But in the long term, if you want the longhand notation here, the steps to consider. First, you got to recognize the salt. So we got to recognize the salt. They typically have the formula something like that, where this is some metal that's positive with some non-metal that's negative. Now be careful, it could also be NH4 plus is your cation, but you're looking for a plus and a minus. Now they don't have to be in a 1-to-1 ratio, but that's what we're looking for. Some sort of positive paired with a negative where that M is not an H. Once you recognize that it's a salt, break up that salt into the cation and the anion. So the positive and the negative. And while you're doing that, look out for some conjugates from strong acids and strong bases, because that'll help make things a little bit easier here. So break it apart into the cation and into the anion. And the reason is these salts tend to be soluble, so they are not stuck together anymore. They have dissociated and are swimming in solution independent of one another. Once you've broken the salt into the cation and the anion, you're going to want to write out some reactions. You're going to want to write the reaction of the cation plus the water to see what happens. And you're going to want to write out the reaction of the anion plus the water to see what happens. Remember, water is the only thing that they can react with other than each other. And then once you have your reactions, you want to look for any strong acids or bases in the product. So we're going to look in here to see if there are any special cases of strong acids or strong bases, because that'll influence our outcome here. And then lastly, determine the overall effect. We'll have to combine them and see if it ultimately ends up being neutral. Does it end up being acidic? Does it end up being basic? The easiest way to do this is to repeat this procedure on several examples. That's what we're going to do here. We'll try some examples. NH4Cl. I recognize this first thing. I see a plus and a minus. I recognize it's not an acid because it's not an H plus. So I need to break it apart. And those are my two pieces, NH4 plus and Cl minus. There's my cation. There's my anion. So then now we need to think about NH4 paired with water. NH4 plus cannot accept an H. It's already full and maxed out, but it could donate that H to make H3O plus and NH3. Cl minus doesn't have an H to give, so the water will have to donate the H to Cl minus. And we're left with that. So it looks like the top reaction is making acid and the bottom reaction is making base. But now we got to inspect them a little bit further. Excuse me. First thing, look at the product side. anything special. In particular, look for strong acids or strong bases. There's one. And we know HCl is a strong acid. So the minute you make HCl, it is going to go back 100%. And because it goes back, this will not actually exist, and this will not actually exist. And all you will be left with is chlorine and water. This guy is neutral. Now in the top case, NH4 is a weak acid, NH3 is a weak base, H3O plus is a weak acid, this is a weak base. Since we have all of these species that are relatively weak, there is going to be some equilibrium established where all four will be coexisting because of this H3O plus. This reaction will be ultimately a little bit acidic. You combine the two with something acidic with something neutral, NH4Cl will be acidic. So if you dissolve this in water, you're expecting a pH less than 7. So now let's try another example. KF. Again, I see a positive and a negative. I don't see H. So we're going to have K plus, F minus. Those are my two pieces. Let's react them with water. K plus H2O. Well, you can think of H2O as an H and an OH. So K plus is not going to want to bond to the H plus. That's two positives next to each other. But K could go with the H2O and kick out an H plus. And then in the second reaction, F minus, we're missing an H. So we're going to donate an H from the water. And we're left with that. Now, inspect your products. Do you have any strong acids or strong bases? I see one. That's a strong base. It'll go 100% backwards. These two will not be existing in solution, and you'll just have K plus with water. This part would be neutral. Now, in my second case, I've got a conjugate base, a weak one. I've got water, a weak acid. I got HF, a weak acid, and I got OH minus, a weak base. Those four will all coexist because of the presence of OH. This will be basic. Combining these two, we will ultimately end up with KF being basic, and I would expect the pH to be greater than 7 when you put KF in water. All right, let's keep going. FeBr3. So hopefully we recognize this is another salt. So we're going to have Fe plus 3, Br minus. I'm going to do the Br first. And then we'll have the Fe plus 3. And in this case, we're going to need a couple of waters because we're at plus 3. And on here we'll have Fe. Fe is a positive. It's going to need a negative from the water. So he's going to take the OH from the water and kick out these H's. Now we look at our products and look for anything that's a strong acid or a strong base. There's one. So this is going to go backwards. These actually won't exist. This will be neutral. I look at the bottom reaction. That's not a strong base, but it is a base. I see the presence of these H pluses. This is acidic, so combined we would say acidic, and we would anticipate a pH less than 7. Now this question here, we got that it was acidic, but it turns out that's not the right reaction. This Fe3 plus is a metal ion with a large charge density. So remember, charge density is the charge of the ion over the size of the ion. So Fe3 plus with its high charge, it's a plus 3. So we're looking at a plus 3 up here. And it's a relatively small size, gives it a high charge density. And what that means is Fe3 plus is not just swimming around in solution all by itself. And it's going to do something unusual, and I wouldn't expect you to predict this, but now that I've explained it, hopefully it makes sense. What's going to happen is this. In this case, it's an aluminum, but what's going to happen is that Fe3 plus with that high charge density is going to be attracted to the waters and the oxygen end of the water will attract to make this little cage and this new molecule. And this is a new formula. It's a complex ion. But this is just a Lewis acid base reaction. We have a Lewis acid, we have a Lewis base with the electron pair donation. And then this new product is going to react with another water, just one, not 6. And what happens here is what's being picked in this picture. With the high charge density here in the middle on one of the waters, and actually on all of the waters, the electrons are getting pulled in from these oxygens. And then that makes this hydrogen vulnerable to add itself to a water that's in solution. So from one of these waters, we are going to donate a hydrogen to water, a free water, and we're going to make H3O+. We're going to still have our iron. We're going to have 5 waters where nothing happened, because it's only happened on one. And on one water, if it donated an H, he's now an OH. Now, if originally the ion was a +3, and now one of the waters turned into an OH, that's a -1. So now we're ultimately to a +2. And the key of all of this, notice when this happened, we generated an acid. We would say it's acidic. I want you to notice it's acidic, just like we predicted up here in blue that it was acidic. We still get the same answer that iron bromide is acidic. It just so happens that the reaction we wrote showing it was acidic is not quite right. Instead, what's happening is this crazy thing. You typically see the ions with high charge density tend to be more of the transition metals. They tend to be the +2s, the +3 charges. That's where you'll see this unusual behavior. So what I want you to do is I want you to pause the video, take these 2 problems, NaF and NaCl, see what you can come up with. Are they acidic? Are they basic? Are they neutral? Write out the reactions showing why it's acidic, basic, or neutral, and then we'll compare, and then we'll do some more examples. So we got Na plus and F minus react with water. What can they make? Na needs the negative, so he's going to take NaOH, so kick out an H. F minus, we've already seen this one. Again, look at your products. Do you have any strong acids or strong bases? There's one. This will go backwards. So this and this don't exist. So NaF will have Na plus, but no NaOH. Now looking at the second case, F minus plus water makes HF, we make a bunch of weak acids and bases in their conjugates, so those will all coexist. So because of this OH, we'd expect NaF to ultimately be basic. Now if you were to zoom in on an atomic level, what you would see in this solution is you'd see the Na plus, you'd see the F minus, you'd see the F8, each F, and the water. Those would all be together in solution in addition to the water. And we got the water, and we'd have a tiny bit of that H3O plus coming from the autoionization of water. Now let's talk about NaCl. Na plus, Cl minus. I'm not going to do Na again because it's up there. Cl plus water makes HCl and OH. So it looks like it could potentially be basic, but that's a strong acid. That goes backwards. Neither one of these will exist. Well, the Na didn't make anything new, and the chloride didn't make anything new. So NaCl is actually neutral, And the pH should be 7 if you dissolve salt in water. And the reason is sodium comes from a strong base, it's the conjugate. The chloride is the conjugate of a strong acid, so they won't do any side reactions. All right, pause the video, try these two, and see what you come up with. We got NH4 and NO3 minus, so we're going to do NH4 plus water. We've done this one already. We're going to donate that the H from the NH4 to the water to make NH3 and H3O plus. And then now we'll work with NO3 minus plus water. That'll make HNO3 plus OH minus. Look to the right on the product side. Again, any strong acids or bases. There's one. Those won't exist, so NO3 is neutral. NH4 plus makes that H3O plus acidic, so we would say ultimately we'd expect a pH to be less than 7 for this one. Now NH4CN, we've got our NH4 plus, which we know from above is acidic. Let's do CN minus. We get HCN and OH minus. Check again for strong acids, strong bases. We don't have any. We do make OH, so this is basic. So we've got an acidic component and a basic component. That does not necessarily mean that those cancel and it's a neutral. It's not an acid plus a base always makes a neutral. We have to know how much acid and we need to know how much base. So how are we going to do this? In this case, let's write out the ammonia because we will need that reaction. So the question now becomes, how much OH is made from the reaction with CN minus? And the other question is, how much H3O plus is made from the NH4 plus? To decide that, we need to know where equilibrium lies. Does it lie closer to the products or does it lie closer to the reactants? And to decide that, we need K values. So we need the Kb for CN minus, since it's a base reacting with water to make OH minus. It's a Kb reaction. And we need the Ka for NH4 plus, because NH4 is my acid. It's donating an H to the water to make the hydronium. Problem, you can't find CN minus. There is no Kb for CN minus. But you can find Ka for its conjugate. And if we know the Ka for HCN, we can then find the Kb for CN minus. Likewise with ammonium and H4 plus, there is no Ka, but we can find the Kb for NH3 and then we can convert it. So let's do that. So it turns out the Ka of HCN is 6.2 times 10 to the negative 10. So Kb and that ends up being 1.6 times 10 to the negative 5. Again, small because CN minus is a weak base. Let's do the same thing to find the Ka for NH4 plus. So the Kb for ammonia is that. So then the Ka, we end up with 5.6 times 10 to the negative 10. Notice these Kas and Kbs are pretty different in scale. The Kb, it turns out, is quite a bit bigger than the Ka. And if the Ka value is smaller, then that means it makes even less product. And since the Kb is even bigger, then that means this basic reaction will happen more often than the acidic. And if the basic one happens more often than the acidic, we ultimately end up being basic. All right. Try this example. All right, from the previous problem, we know what happens with ammonium. We predict ammonium will make a solution weakly acidic because it does make some H3O plus. The anion here is CO3 minus 2. We're going to react with water. You can only protonate one at a time, so we're going to only add one H. And then we've got some leftover OH. Check our products for strong acids or strong bases. We don't have one. And I got an OH, which says it's basic. So we've got competing acid and base, so we need to compare the strength of the first reaction, how much it goes forward, to the second reaction, how much it goes forward. And to do that, we need to compare equilibrium constants. Well, in the previous problem, we found the Ka for ammonium was 5.6 times 10 to the negative 10. That will still apply here. So for this reaction, Ka for ammonium was 5.6 times 10 to the negative 10. So now for the second reaction, we need Kb of CO3 minus 2. Problem, there is no Kb. And if you go look up HCO3 minus, there's no Ka value for that. What you can find is H2CO3 has a Ka1 and a Ka2, where the Ka1 is 4.3 times 10 to the negative 7, and the Ka2 is 5.6 times 10 to the negative 11. Now, in this second reaction here, I'm going back and forth between CO3 2 minus and HCO3 minus. So this is the losing or gaining of that second H. That's the Ka2. So we need to find Kb for that reaction using Ka2. So Kb here is 1.0 times 10 to the negative 14 divided by that Ka2, 5.6 times 10 to the negative 11, which gives me a 2.1 times 10 to the negative 4. So comparing my Ka and my Kb again is way bigger than my Ka. Because my Kb is greater, it'll make more products. If I've got more products, I'm going to have more OHs in solution. And this solution ultimately ends up being basic.